Alright, welcome to another video on waves and oscillations. So we're going to be talking about now a damped system. So a damped system is one in which you have a spring and a damper. So the damper is just a device that absorbs energy. In this case, it could be something like a cylindrical drum containing some kind of dense liquid like oil. So if this thing tries to move away or towards the direction of the wall here, a lot of that energy is going to be transferred to in the form of heat to the liquid inside, and it is essentially going to be absorbed. So in this system, you would never observe simple harmonic motion simply because the presence of some energy loss mechanism is going to ensure that the total energy decreases over time. And the rate of decrease is going to be dictated by how large the damping constant or the damping factor here C is compared to the restoring force and so on. So if we draw the free body diagram of this system, essentially we get this. So we have two restoring forces, one for the spring, one from the damper. So the damping force is always proportional to velocity. And over here we have the net force of the body, which is mass times acceleration. Using Newton's laws of motion, we can derive the following equation of motion along the x direction, which leads to the second order differential equation we have here. And using a similar technique to what we used in the previous two videos, we can just divide by the mass, and then we can replace this by two other constants. So in this case, I just call this gamma, which is a damping factor, and this is the natural frequency of oscillation, omega naught squared. Now, we're going to write the equation in this form, and it has its own corresponding characteristic equation since it is homogeneous and linear with constant coefficients. This leads to the two roots, which can be obtained using the quadratic equation. So we have minus gamma plus or minus the square root of gamma squared minus 4 omega naught squared divided by 2. So this is essentially what we have right now. And what the interesting thing about this system is that we're actually going to have three different types of solutions. So it's going to depend on the value of this thing over here, which we call the discriminant of the quadratic equation. So let's consider a few cases. Case 1. We would consider the damping factor to be a lot larger than the natural frequency of the system. And what that essentially means is that this would be extremely large compared to that. What that means mathematically is that if we look at the term here, which is the discriminant, if this is much larger than that, then this is essentially the same as saying taking the limit as omega naught goes to 0. So this is the same as approximating this expression by just gamma squared, which leaves us with just gamma. Now, if we plug that into the equation here for the roots, we obtain two solutions for the roots, 0 or minus gamma. So plugging that into the solution or the general solution of the equation, we obtain this. Now, what happens now is that we have this expression here, which is a decaying exponential or an exponential decay function. So if we look at this system, if we plot it against time, we notice that this is just going to quickly decay and essentially the oscillations will not even take place. This would just start off at some initial displacement a plus b, and it would just go all the way to 0 very, very quickly. So that's all this is telling us. And how fast that happens is going to be dictated by the damping factor, which we know is just going to be the ratio of the damping constant to the mass. Okay, so if the damping constant is very large compared to this, then this overdamped system is just going to decay very quickly, which means that if we try to visualize that motion, let's say you release this from the right, this is just going to come back very slowly to its original position, and it is not going to actually move back and forth at all. Case 2, which is very rare, is when both of these are actually equal to each other, which means the discriminant is 0. Now we're going to have two distinct solutions that are essentially the same. But the function in itself is not going to change very much. We still have a damped and overdamped system, so it won't oscillate back and forth. We're going to have this general solution corresponding to the theory of linear differential equations. So nothing much interesting happens here, and in fact it's very unlikely that you will ever encounter this in physical systems. You will never have damping factor equals to that. Very unlikely situation. Now the most likely one is when the damping factor is a lot smaller than the natural frequency, in which case the discriminant of that quadratic equation is going to be approximated by this. So if this is a lot smaller than that, we can make it equal to 0, and then we approximate it by this. And you notice now we have a negative sign under the square root, which implies we're going to have complex numbers or a complex root, which we can write in the form I to omega naught. Now plugging back into the equation for the roots, we're going to get this expression over here, which can be decomposed into the real and imaginary parts. Now, what do we do with that? Well, it turns out that this is actually quite an interesting system, because now we have the general solution over here has a decaying exponential function, but it is attached to two periodic functions, so cosine and sine, which implies that this system is going to be damped, so it is going to oscillate back and forth, but there's an envelope function that is going to decay the oscillations. It's going to make them decay over time. So essentially it is going to be doing this. So you can imagine that the mass itself, it is going to come back to its original position, then it's going to move a little bit to the left, but then it's going to go back and move a little bit to the right. So it's kind of like a pendulum that is coming to a stop very quickly. And depending on the relationship between that damping factor and the natural frequency, this decay can be a lot faster, or it can occur over a longer period of time, depending on that. So this is essentially what we're going to have in most cases, and what we call a damped system. So hopefully this has given you an idea of what is actually more physically practical, and this is the kind of stuff that you would observe. So damping usually corresponds to any energy loss mechanism on the environment. It could be something like air resistance acting on the system, some fluid surrounding this that would absorb energy, perhaps heat, friction on the wheels or with respect to the surface. Anything like that that you can think of is going to impose damping into the system. So we will never see the energy, the total energy of the system is actually going to decay over time, as we would expect from any realistic physical system.